Welcome everyone. Today we are going to be describing a chemical conversion process that describes the production of styrene from butadiene. And the team that made this project possible includes Paul Blankard, Amelia Conti, Gabby DiBattista, Seth Kodner, Joshua Meisenhelter, Jessica Callahan, and Seth Temple. So the main focus of this presentation is really to just provide an overview for the feasibility of a knit-line chemical plant that we are trying to integrate this chemical conversion process for converting butadiene into styrene. So at the beginning of the presentation, we're going to be focusing on project background and the rationale. And then eventually we will go into the process itself and the various specifications that we were looking into. And then we will discuss the economic feasibility of this project. So we are Knit-Line Chemicals, and we have an existing plant that is situated on the Gulf Coast in Houston, Texas. And what we aim to do is modify this plant so that we can convert unsaleable C4s into saleable styrene product. So the main goal of this project is to be able to increase the olefin capacity of gas oil feeds that contain C4s and also 1,3-butadiene. So since the demand for 1,3-butadiene has been steadily decreasing, in this project we aim to develop a new and highly reliable chemical conversion process that takes this butadiene and converts it to styrene. And for this chemical conversion process, we have two main reactions that are going on. The first is a dimerization reaction of 1,3-butadiene to produce vinyl cyclohexene. And then the second is an oxidative dehydrogenation reaction that converts vinyl cyclohexene into styrene. So by optimizing these chemical conversions and performing product isolations from undesired byproducts, we have been able to design a plant that can successfully produce 488 million pounds per year of styrene from 140,000 pounds per hour of C4s. In addition, we have been able to isolate and purify benzaldehyde and fuel gas in order to increase the overall profitability of this plant.
Our process begins by setting our C4 feed into the proprietary extractive distillation column. This is done because our own modeled column for this separation had a much higher capital cost and resulted in a less pure butadiene feed. The pure butadiene feed is then sent into the first reactor, where it's reacted into vinyl cyclohexane, or VCHX. We also produce a side product of cyclooctane. For this reactor, we actually have two reactors. The one will have the actual reaction going on, and the other one will have the catalyst being regenerated at any given time. The products from this reactor are sent to a butadiene recovery column, which sends the butadiene back into the feed as a recycle stream. This is done to increase conversion. The products are sent on to a cyclooctane distillation column to remove the cyclooctane. This is done here because cyclooctane and styrene are pretty close in boiling points, so a separation later would be much more costly and result in a bigger column. The purified VCHX is then sent on and combined with water and oxygen before being sent into the second reactor. For this reactor, we needed a large enough volume that we actually have 3 reactors in parallel, as well as a 4th to regenerate catalyst. In this reactor, we're producing styrene, but we're also producing side products of ethylbenzene, benzaldehyde, and benzoic acid. These products, as well as the unreacted reactants, are sent in onto a liquid-liquid extraction unit. This is done because the water and styrene actually form an azeotrope, so separation is a lot more difficult if you use a column. The LE sends the styrene, ethylbenzene, and some benzaldehyde through, but the water, as well as the CO2, benzoic acid, some benzaldehyde, some ethylbenzene, and the oxygen and argon are sent on either back into the recycle to reduce water costs, or to a secondary LE unit in order to treat the water. This is done because the water going out of the LE unit has too many organics to be sent to wastewater treatment, so instead we use a flash column and then an LE using pentene to reduce the organics to a reasonable level. The products are sent forward and combined with an inhibitor. This is done now because the inhibitor is soluble in water, so if we'd done it before the LE, it would have left with water. We have one column to separate the VCHX out and send it back and into recycle. And then we have a series of 3 columns. The first to separate out ethylbenzene, and this is done because ethylbenzene and styrene are pretty difficult to separate, so we need 2 columns in order to make sure that neither one is excessively large or has an excessively high reflux ratio. Our final column separates benzaldehyde and styrene, and both of these are sellable products at this point.
Overall, our process is very effective, producing saleable qualities of both styrene and byproduct benzaldehyde, as well as utilizing our waste streams as fuel gas. As you can see, we are able to achieve a styrene purity that is higher than the necessary 99.8% in order to meet customer specifications. Additionally, all of our impurity levels of ethylbenzene, olefins, oxygenates, and water are well below the threshold values. Additionally, our benzaldehyde side product meets the specifications required for sale of 99.5%. And lastly, all of our waste streams, with the exception of 2 purge streams that end up going to the flare, meet the required heating capacity value of 6,500 BTUs per pound in order to be used as fuel gas to gain additional profit. From an environmental standpoint, we are also meeting the specifications here. So we have a pre-treatment wastewater system to lower our organic levels down below the threshold value of 5,000 ppm. And this wastewater is then sent to an additional treatment facility for treatment prior to being sent back out into the environment. And we also meet emission standpoints by sending our waste gases to the flare in order to reduce any potential emissions. From a safety standpoint, safety is really important to our company, so we have a lot of measures in place in order to assure that our company is operating safely. First of all, we have assured proper materials of construction for all of our equipment. Any equipment that's in contact with benzoic acid, which is corrosive, is made out of stainless steel in order to preserve mechanical integrity and prevent failures. Additionally, we have significant process control throughout our plant to assure that everything in the plant is running smoothly, and that if there's any type of upset in the system, the operators are immediately alerted, and we even have shutdown alarms to shut down the process if there's a significant upset occurred. We also have pressure relief valves located on all of our equipment in the case of overpressure, which vent to a flare header so that these vessels don't overpressure and burst. Lastly, we have a very strong safety culture at our plant, and in order to assure that our operators remain safe, all personnel that go out into the plant must wear personal protective equipment. We even have specialized personal protective equipment depending on the particular hazards in the area that they'll be encountering. In particular, in areas like the extractive distillation unit, where there's the potential for cyanide compounds, our operators must wear monitors that have both the capacity to monitor LEL as well as cyanide to prevent the operators or personnel from encountering any dangerous conditions.
As Gabby mentioned, this plant meets several of the hard environmental and safety specifications. However, there are several soft specifications that have not been met and that need to be discussed further in detail. Foremost, we were given the target that only 2% of VCHX or VCHX product should be leaving the process through waste streams or byproducts. However, currently 13% of VCHX is leaving our system. This is due to 2 primary reasons. The first is VCHX or styrene lost in purge or waste streams. This happens because of recycle streams, which require purges to ensure that the material is not building up in the equipment and harming the equipment. The second reason is that in the ethylbenzene and styrene purification steps, that separation is very difficult, requiring a lot of styrene to be leaving the tops of the ethylbenzene styrene separation columns. The second reason that we're not meeting the VCHX loss performance target is because of byproduct-related loss, which accounts for 6% of the 13% total. This happens because of the constraints set forth by the selectivity and conversion through the styrene reactor. There will always be some portion of ethylbenzene, benzaldehyde, and benzoic acid that are being produced through that reactor based on reaction constraints. Therefore, it's impossible to completely eliminate that type of loss. However, it is notable to mention that 2% of that loss occurs because of benzaldehyde sale, which means that we are making money from some of this loss. Furthermore, we were given the task of limiting the energy use in distillation towers to approximately 145 MMBTU per hour. However, what we currently use is 186 MMBTU per hour. This occurs for two major reasons. The first is the styrene purification step, which is obviously important because we need it to make sure that the styrene that we're producing is saleable to our customers. The second is the ethylbenzene processing step. Because of the difficult separation between ethylbenzene and styrene, 2 distillation columns are actually used in this process. Now, it is very important to have both of these, but it can be potentially optimized in future iterations of the plant in order to decrease the energy usage. In addition to the specifications, economics are also an important part of this process. The IBL cost contribute a lot to the total capital cost, accounting for approximately 55%. This is due to 2 primary reasons. The first is our extracted distillation column, which takes up 39% of the IBL cost. These columns have a these proprietary columns have a high cost associated of about $135 million, which added to the contingency is even more for our plant cost. Additionally, we have other equipment that accounts for a lot of the capital cost, which includes compressors, which are necessary to ensure that the recycle streams are meeting specifications to go back into the system.
Every year for our plant, the raw feed material cost was very high. As you can see, the highest cost is due to just the plant transfer of C4s. That makes up 84% of our feed prices and material costs every year. To reduce this, we can look into different methods of transporting our C4s. Even a fractional reduction in cost will increase how much money we'll make by a significant amount because of the large volume we're buying. The next highest is our N-pentane, which is used for water treatment. This could be reduced by looking into more effective methods of water treatment than equilibrium liquid-liquid extraction. However, that's outside the scope of this project. And another yearly cost are our utilities. Many of the utilities that we have, such as the steam generation and steam use, are fixed and can't be changed too much. However, to offset that, throughout our process, we can generate steam. As you see, we generate high pressure steam to offset some of this, but we could also generate more power through implementation of turbines in areas where we have large pressure drops through the system. This would generate more power because currently we are just venting to the atmosphere to reduce pressure. Our highest utility cost comes in wastewater treatment. This can be reduced by looking into, again, more efficient methods that are outside of the scope of this project. When scaling the prices of our utilities, we use the prices based on the price of natural gas per unit energy. So by looking at the future projections of natural gas prices, we expect that up until production begins, our utility costs will remain fairly constant, and we can keep the numbers that we use with some degree of confidence.
For our plant, we determined the total annual fixed cost to be $70.1 million, with 54% of that coming from the proprietary separation technique. And that 54% accounts for the licensing and the operating costs for our proprietary separation. In addition to the proprietary separation, the rest of our costs come primarily from property taxes and repairs and maintenance, with the remainder coming from labor, overheads, and insurance. As I mentioned, the total annual fixed cost was $70.1 million. We also determined the annual expenses and profits for our plant. The total annual profits came out to be $386.8 million. The majority of this is coming from our main product stream, which is styrene, and the rest is coming from our 2 side product streams, benzaldehyde and fuel gas. The majority of our side product profits are coming from the fuel gas, which is 16% rather than 2% or 2% for the benzaldehyde stream. We determined our total expenses to be $376.9 million, and the majority of that is coming from the purchase of our raw materials. The remainder of our expenses streams is primarily the fixed costs and the utilities, and the remainder coming from the wastewater and the SG&A costs. We determined our total net income would be about $9.8 million, so we are slightly positive for that figure. Using our cash flow model, we also looked at what our cash flow would look like every year over the lifetime of the plant. And after accounting for depreciation and capital costs, it is actually generally negative most of the years. And this resulted in a total cash flow, cumulative cash flow in the year 2036 of negative $238 million.
To produce a recommended after-tax rate of return of 20%, it is recommended that we increase the styrene sale price to 90 cents per pound. Looking here at the net present value graph, we see that it's a linear function, and it's juxtaposed against the after-tax rate of return, which is approximately modeled as a logarithmic function. If the United States historical styrene market is any indication, it is unlikely that we will reach this target of 90 cents per pound, as the last 18 months show a trend unable to reach this 90 cent threshold needed for profitability. In conclusion, under the conditions outlined in our base case, we think it is unfeasible to recommend moving forward with construction of this plant. However, the base case is a significant improvement over purchase of the raw materials alone, and even better, there are some alternatives that we have explored that would eliminate the proprietary extractive distillation method of the incoming C4 stream and replace it with an in-house designed, licensing-free, Knitline Chemicals designed extractive design. Overall, we explored these options in order to make the best business decision to deal with this C4 stream in subject. Thank you.